What's the charge on your metals? Positive. What's your charge on hydrogen? It's positive, most typically. So what we're doing is exchanging our cations. That cation is usually a metal, but it doesn't have to be a metal. Okay, so if we go through and look at that first reaction problem, what we're going to do is swap. We're going to have iron with our chloride, and we'll have hydrogen. Before we do anything else, what we've got to do is make sure our formulas are balanced. Okay, so we take a look at iron and chloride, and we say, is that formula balanced? Okay, to know if it's balanced, we need to know the charge on both of those species. Do we know the charge on chloride? Yes. How do you know that? It's memorized, periodic table, whatever you want to do. Do you know the charge on iron? Why? Because I gave it to you. I said iron was supposed to be a +2. So if we look at that formula, would our overall charge be 0? No. So our formula is not balanced. So we have to balance our formula. What do we need to do to balance the formula? We need more chlorines. Okay? In fact, we need 2 of them. That 2 shows up as a subscript after the chlorine. Not before it, not after it in a big number. Okay? Subscript immediately after. That applies to what's immediately in front of it, which is the chlorine. There are now 2 chlorines, which gives us an overall charge contribution from the chloride of -2 plus 2 gets us 0. Our overall charge is correct. There's our proper formula for our iron chloride. Technically, our iron 2 chloride. Okay? How about our formula for hydrogen? Also not correct. When we're talking about hydrogen showing up on its own, it needs to be H2 because it is diatomic. I tend to not be a big fan of phases, but we could push phase information in on this. H2 is typically a gas. As far as the FeCl2, we would probably guess that we're looking at aqueous, okay? Just because that matches the format we've already seen. Okay? Could it be something else? Yes, we'll talk about that maybe by the end of today. Okay? Next one.
Question.
Yes?
Is it okay to put the hydrogen before the Fe?
2 plus 1 is 3. What is 1 plus 2? 3. Does the order of addition matter? Nope. Same deal here. The order does not matter. We can put the hydrogen first. Okay. Next one, we go through and do the same process. We're exchanging gold for our hydrogen. We have AuSO4 and we have H. Why do I not write H2 right away? Or said another way, let's try that again actually. Our formulas now need to be balanced. Is our formula for hydrogen balanced?
No.
No. What does it need to be?
H2.
H2. The 2 in H2 compared to the 2 in H2SO4. Do those have the same meaning? No. Just because the number is the same does not mean the meaning is the same. Okay? So I have H2 in the product not because I have H2SO4 and my reactant. I have H2 in the product because hydrogen by itself needs to be hydrogen gas, which is H2. Why do I have H2 in H2SO4? To balance hydrogen against sulfate. Entirely separate reasons for those numbers. You have to be aware of that. We're not just swapping numbers across. Is gold sulfate balanced? The charge on gold was +1. The charge on sulfate, -2. So it's not balanced. What do we need to do? We need 2 golds. So we'll put the 2 as a subscript immediately after the gold. We could again drop in the phases. Again, I don't really care, to put it somewhat bluntly. Last one. Same process.
We need to balance the reactants.
We'll get to that actually in a second here. Okay. So in this case, all we've done is gone through and predicted the products. I have not balanced the equations. All I want to know is what are the products. So it's a simpler question, at least at first, is can we accurately predict what our products are? Okay? And that's all we went through and did. When we look at the copper as our final product, what is the charge on the copper? what is written in the upper right-hand corner?
Oh.
Nothing. What is the charge on the copper?
Nothing.
0. Okay. What is the charge on hydrogen in our product?
0.
Also neutral or 0. How do we know that? There's no charge written in the upper right-hand corner. It's one of the characteristics of a single replacement reaction. Okay. If we wanted to go through and balance these, sometimes our single replacements are sort of trivial if you want to call it that way to balance. We just go through and balance the elements like we have on every other reaction. So in our first case, for some reason I already gave you the 2, but in that first equation, it's already balanced, right? We got 1 iron on both sides, 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines. Everybody okay?
Yeah.
Second reaction down, is that balanced?
No.
All right, what's wrong with that second reaction?
Gold.
Gold isn't balanced. So I can put a 2 in front of the gold. Now that I'm balancing the equation, I can use the capital numbers, regular numbers, and we'll put those as our coefficients in front of each of our values. What is that?
It's a resonance.
Not resonance. Okay. Last one. Is it balanced?
No.
What's missing?
Gold.
I need 2 golds. Again. Okay. I don't know why I just did that color change. Okay. Last part of this is, which is what we started to get to at the end of lecture on Thursday, was deciding if the reaction occurs. To decide that, you have to look at an activity series. So what we just went through and did is just said, hey, let's just call a reaction happen, let's swap it, let's see what our products are. Okay. Now that we've got our products and our potential for a reaction, now we want to decide, did that reaction actually go forward? Okay. And that comes back to looking at our activity series. The higher on our activity series, the more it wants to be an ion. The lower on the activity series, the less it wants to be an ion. So what we would go through and do is look at the species that's changing from ion to not ion and see what happens. So our second equation, let's do with our second equation. What are the species changing from ion to not ion?
Iron.
Iron is going from 0 in the reactant to
+2.
+2 in the product. So it changed its ion state, 0 to +2. Okay. What's the other species that changed its ion state?
Hydrogen.
Hydrogen went from +1 to 0. So those are the two we're comparing. We're comparing iron to hydrogen. So we go up to our activity series and we find iron and hydrogen. Right? So we've got our iron here, and we have hydrogen here. Nice big bold letters. Right? According to that ranking, iron wants to be what? More ion or less ion? More likely to be an ion. Why? It's higher than hydrogen in the activity series. So we now go to the equation and say, where is iron an ion? Where does it have a charge? As a reactant or as a product? As a product. Iron wants to be an ion. So what is iron going to do? In this case, it will react with hydrochloric acid because then it can become an ion. This reaction occurs. Okay, so by having the equation in front of us, we can now compare which one wants to be more like an ion. Where is it most like an ion? On the reactant side or the product side? If it's the product side, the reaction goes forward. What if it's on the reactant side? It's not going to happen because it wants to be the ion. It's already an ion. If it does a reaction, it's no longer an ion and it doesn't want to do that. Right? Do we have to look at it wanting to be an ion? No, we've got another option. It could be less like an ion. So let's evaluate hydrogen. Hydrogen does not want to be an ion in comparison to iron. So let's look at our reaction. Where is hydrogen not an ion? On the product side. Second piece of evidence supporting that the reaction proceeds as drawn. Okay? We fully expect that reaction to occur. And we come to that conclusion by interpreting the activity series. How about the next reaction? So we'll go through the exact same process. What do we need to evaluate?
Gold.
We're comparing gold, which started as what charge?
+1.
How do you know it's 0? Upper right-hand corner. There's nothing written, so our gold starts as a 0. And it goes to, now it's our +1. Okay? The +1's a little bit trickier. We technically have to solve for it or know how we got that charge from it. But we do know that the gold there has to be a +1 to balance out the sulfate. Okay? What's the other species? Changed its state. Hydrogen. Hydrogen went from +1 to 0. So we again are now going to go back to our activity series and compare. Except now what I want to compare is hydrogen to gold. So when I do that comparison, which one do I want to look at? Hydrogen or gold? Okay. Gold. Does it want to be more like an ion or less like an ion in comparison to hydrogen? Less ion. So I now go to my equation. Where is gold less like an ion? Reactant side, which means does this reaction progress forwards? No. So we went through all that trouble to write out and balance that equation. And really what we would expect to see for an answer, where's my eraser? There it is. NR for no reaction. Okay. Did balancing it out hurt you? No, it gives you the practice and it allows you then decide, is it more like an ion or less like an ion? It gets you to the answer, in my opinion, quicker, okay, and more consistently. If you want to try other methods, that's fine, but balancing out or at least attempting to do your single replacement helps. Okay. What about the last one? We're comparing gold to copper. What do we expect for the last one? Again, no reaction. So that was a fun little question, right? Really all you had to do is write NR twice and give me FeCl2 plus H2. Wasn't that hard, except you had to know all the chemistry. Okay. What happens if I do not give you the activity series? Interesting phrasing on that. What's that? So you might as well go through and try and balance it out anyways, okay, and see what's going on, because maybe what the question is asking is just what could it potentially turn into. We aren't being asked, did the reaction occur or not. We're saying, can you do it? Okay, and if you can't, if it's something you can do, then yeah, you should go ahead and do it. Okay. When it comes to the exam, you are given an activity series. Is it this exact activity series? No, because that's got a lot of stuff on it that I don't want to type up. What you will be given is a shortened activity series with probably 5 or 6 elements on it. Okay. Will it have just the 2 elements that I ask questions about? No, because the idea is to make it a little bit broader and give you something to interpret. Okay. So if you take a look at practice exam 3, you will see a modified activity series. Okay. You need that activity series to solve these types of questions. Question, yeah.
So, in theory, if gold is in the reactivity, it never is going to react? Is it nothing like
Never reacts because it's lowest on the activity series. Okay, and I don't remember if we started to go into this or not. What is the standard that all currency is based off of?
Gold.
Why? Because it doesn't change its state. Let's envision that we said instead of gold, lithium was our standard for all currency. Okay? What happens to Fort Knox? Well, someone comes in, lights a match. The match turns on the sprinkler system. The sprinkler system drops water, hits the lithium, and the lithium instantly turns into ions and now dissolves. And there goes your financial system. Okay? And it gets more dangerous than that too. But that's beside the point. We still lose the metal. gold is our kind of standard of currency because we have a sizable amount of it in comparison to some of the other metals, and its activity is exceptionally low, which is why we use it as a currency, because I don't want to take my gold doubloon or whatever and walk into the store and give it to them and then have them accidentally spill an acid on it, and now I don't have that money anymore. I want something that actually holds some value and does not disappear on me. That is why gold is a currency, because it has no activity. Can we get gold to dissolve into ions? Yes. We need very special reagents and conditions to do that. As an interesting side note, it was a Nobel chemist, I believe, circa World War II, I believe in one of the bad places to be during World War II, was noticing that the Nazis were going to come in and take over his lab. Well, he has this massive gold medal from winning the Nobel Prize. Okay? What's the first thing the Nazis are going to do when they see a gold medal? Take it, melt it down, and steal it effectively. So what he did is he dissolved it into an ion or into a solution. Then he put that jar on his shelf and he left. Came back after the war, there's the jar still sitting on the shelf. Reversed the reaction, he had all his gold. Okay? So there are ways that you can manipulate gold, but it requires very toxic and dangerous corrosive chemicals that we typically don't want to have access to.
Reverse it to a solid state?
You can reverse it back to a solid state. All chemical reactions are reversible given the proper conditions. Those proper conditions can get a bit nasty. I doubt you will be able to try that. Okay. The material used is known as aqua regia, which translates into the water of gold, because what that material does is it dissolves gold and turns it into an ionic state. Okay. Kind of a neat process. Questions? The water doesn't react. So when we went through and looked at these, iron went from a 0 to +2, right? How did it change that charge? What has to happen to the iron to go from 0 to +2?
Trades electrons with.
It has to trade electrons. What did it trade electrons with? Hydrogen. What we're looking at here is what's known as a redox reaction. Reduction coupled with oxidation. This shifts us into chapter 17. Almost. The last thing your textbook mentions is this thing called active metals. Some metals are so reactive that if you add water, they turn into ions. Ta-da, that's about it. Okay. I don't think I would ever ask a question on that because it's just kind of dumb.
What's mineral oil?
Mineral oil is something else entirely. It's petroleum, effectively. It's a carbon-based product. So, reduction and oxidation. Any reaction that involves the transfer of electrons from one, and this is where it's going to get weird, unit to another unit is referred to as a reduction and oxidation reaction. Okay? So we have to look for things that help us identify if it was a reduction and oxidation reaction. One thing that we've already started to do was to look at our quote-unquote charges. What is the charge on calcium in our reactant? 0. What is the charge of calcium in our product? I don't want 2. Plus 2. How do we know that? What's the charge on calcium hydroxide? It is 0. That has to equal the sum of the charges of all the things that make it up. What is OH? -1 is fair. I'll even sort of accept -2. I want the name. Hydroxide. It's one you are required to know. Hydroxide has a -1, you got me doing it now, charge. But how many hydroxides are there? 2. Plus the charge on our calcium. Well, we don't know the charge on the calcium. How many calciums are there? 1. So I get X -2 equals 0. What does X equal? +2. Okay. So what we're doing is solving for the quote-unquote charge of the calcium in our product. Okay. Yes, you can do some of that by inspection. What happened to the calcium? Well, to go from a 0 to a +2, what happened? Why did it lose 2 electrons? Why didn't it just gain 2 protons? We can't change the number of protons. That changes the element. So all we can change are the electrons. Right? But a loss of 2 things, shouldn't that make it more negative? If I lose money, I go into debt, right? That's kind of a crappy thing.
It's because they're negative.
It's because the electrons are negatively charged. Right? So I'm not losing money, I'm losing debt. Losing debt is a good thing. Okay? We move up in our monetary values. Same thing's happening here. Okay? What happened to our hydrogen? Started as officially a +1. We'll kind of deal with your charge in a second. And it became 0. How does it go from a +1 to a 0? It gained 1 electron to go from a +1 to a 0. But I got smaller by gaining things. Again, what did you gain? A negative species. Your number should get smaller. Okay. You'll notice that as we've got this written, do our electrons balance out? 2 electrons, 1 electron. They do not balance. So we would expect to see electrons showing up in this. That's a bit problematic. Why? Electrons are tiny, vicious, nasty little creatures that cannot exist on their own. Right? You can envision them as parasites. They will never leave something else. Right? So I can't ever see it on its own. So how did this reaction occur? Because if we look at it, it's balanced. What's going on? How many hydrogens were converted?
2.
Okay. The conversion of those 2 hydrogens means, whoops, not 21 electrons, but 2 times 1 electron. And I gain 2 electrons through the course of the reaction. Okay. So what we're looking at is the balance of those, at least at this stage we're calling them charges. We're about to change that. Okay, to decide that we have a reduction and oxidation reaction. Okay, they are coupled with each other because I cannot have a reaction to produce electrons because electrons are parasites. They cannot be by themselves. I cannot have a reaction just consume electrons because I never get electrons by themselves to be able to consume it. So what ends up happening is I partner those 2 reactions with each other. So the one that produces electrons immediately gets consumed by the one that consumes them. Okay. Questions on what's up here? Okay. Redox reactions don't involve charge. It all comes back to oxidation state. This is kind of an odd concept because we've kind of dodged and danced around oxidation state and in certain cases have just blatantly called it charge incorrectly. Okay. The oxidation state applies to an atom. The charge applies to a unit. Okay. So let's take a look at the oxidation state and the charge for that first species. What is the charge on that first species?
0.
How do you know it's 0?
Nothing specified.
The charge is always written in the upper right-hand corner, and if we see nothing, the charge is 0. What's the oxidation state? The oxidation state must now apply to the atom in that unit. Well, what atom is in that unit? Calcium. Is there any other atom there? Guess what happens? The oxidation state equals the charge because there's nothing else present. And our oxidation state, or our oxidation number, I will be going back and forth between those because I can never decide which one I like better. Okay, equals 0. It would be nice if we had some kind of formula to allow us to always solve with what the oxidation state was. Okay, well, there's a nice little simple formula we've already been using. The overall charge on our unit is equal to the number of our atom times its oxidation state plus the number of the next atom times its oxidation state, and so on and so on. That looks really familiar, or at least it should, because we've used that before, except instead of calling it oxidation states, we called it charge. Okay? So when I said you should be using this formula because you need to understand what it means, this is where what it means becomes relevant. We're looking at the oxidation state for our elements. And it becomes even more important for us because the oxidation state we can now apply to all atoms.
Where is it shown? Where do you write it on the
It is not written in your formula. The charge is written in your formula. You have to solve for the oxidation state given the charge. Given the complex ion SO4-2, known as sulfate, I could ask, what is the charge on sulfate? And you would all tell me, -2. I now have the option of saying, what is the oxidation state of the sulfur? That is one you have to solve for. Okay? And there are certain rules that you are forced to follow to do that solving process. Okay? These are our rules. Okay? The book lists all of these rules out. I would actually modify these in just a second. Any atom in its elemental state has a 0 oxidation state. Okay? Well, that's because all by itself, what's its charge? 0. Well, the sum of the oxidation states equal your charge. If your charge equals 0 and you're all by yourself, your oxidation state equals 0. For any monatomic ion, the oxidation number equals the charge on the ion. So that means what if I asked you for the charge on magnesium ion, you would tell me it is charge on magnesium ion plus 2. What is its oxidation state?
2.
Plus 2. Same thing. Okay. Where we then run into some issues is what happens with our nonmetals. They are typically negative, okay, but there are some massive exceptions to when they can be negative and when they can't be. Oxygen, being exceptionally electronegative, will always carry the negative charge. It is always a -2 oxidation state. Yes, there's an exception. Don't worry about the exception. Oxygen is a -2 oxidation state every time you see it. Hydrogen, very typically a +1 oxidation state. There is an exception when it's bound to metals. Why? The electronegativity between hydrogen and a metal. Hydrogen, more electronegative than your metals. So it will take the electrons away, thence giving it the negative charge. Halides will always be a -1 charge. The exception again, rule 3A, except when bound to oxygen. Oxygen will always be a -2. The last part of this is that the sum of the oxidation numbers will equal the charge on the molecule. And the charge is always, always, always given to you. So that allows you to solve for them. Okay? Is that a question?
I'll leave talk to class.
Okay. Modified oxidation state rules. Know the charges from ionic compounds. So remember when we told you to memorize the polyatomic ions? I told you needed to know the charges on the polyatomic ions? Know those charges. Okay? You still need to know them because you have to be able to calculate the oxidation states of the elements within those compounds. Oxygen will always have a -2, and then the sum of your oxidation numbers equals the charge of the unit. Okay? So really just 3 rules. Okay? Where things get a little bit weird is your unit can be a molecule, it can be a compound, it can be an atom, it can be a complex ion. Your unit can be anything. Okay? But that unit will be somehow given to you. So, let's take a look at some examples. Charge. What is the charge for those 4 units?
0 might be 1.
Right. Theoretically, this stepwise is nicely and out of sequence. We look at the upper right-hand corner, we now know the charge for each of those units. Okay. Now the tricky part, the oxidation state. Okay. What is the oxidation state for each element in that same set. Okay. Give you some time to work on this. If you got questions, raise your hand. I'll come to you. Hopefully those first two are straightforward and you've already got those solved. The last two might be a little bit tricky. The oxidation state. Okay? The oxidation state is never given to you. You must solve for it. Okay? Yes, that solve, you're like, oh, that's a silly equation. Yeah, you're right, it is a silly equation, but if you go through and always solve for it, you'll never run into the issue of going, oh, should I solve for it or not? If you're always solving for it, you will always get the correct answer. So the oxidation state for Cu, well, there's 1 copper times its oxidation state, and that must equal the overall charge. What is the overall charge for Cu? 0. So 1 times x equals 0. X equals 0. I now know the oxidation state for my Cu is 0. Do the same thing for the Cu plus 2, except what's the big change? The overall charge now is not 0, it's plus 2. How do I know it's plus 2? Upper right-hand corner, it says plus 2. When I go through and solve for the oxidation state, I get plus 2. It comes out the same. If we go through and now move to NO3 minus or SO4 minus 2, our nitrate and our sulfate, we now have a problem. Our oxidation states apply to an element. Okay? Nitrate is a complex ion made up of 2 elements. Which means if I ask for the oxidation state, you need to give me the oxidation state for both the nitrogen and the oxygen. Okay. What is the oxidation state for either of those? Oxygen's a minus 2, and you know that because it is always minus 2. Has nothing to do with it being diatomic. I think I just heard that. It has to do with its balance of electrons and its reactivity overall in the grand scheme of things. Okay? You just need to know that it's a negative 2. Okay? So we can now go back to our formula. The number of our nitrogens. How many nitrogens are present in nitrate? 1. So 1 nitrogen. I don't know the oxidation state for our nitrogen, so it's X. Plus the number of oxygens. How many oxygens are there? 3. Times its oxidation state. What's the oxidation state for carbon, that element? A negative 2. That has to equal the overall charge. The overall charge in this case is, why is it negative 1? The superscript after the nitrate. The charge is always, always, always given to you. Okay. Can you now solve for x? Yeah. And in theory, you should get x equals plus 5. Okay. Questions? I'll accept that as a no. How do we do the sulfate? Do we want to see the sulfate? Okay, so let's do the sulfate. What's our oxidation state for any one of those? The oxygen oxidation state is always negative 2. How many sulfurs are there? What's the oxidation state of sulfur? Unknown. Plus, how many oxygens? What's the oxidation state? Has to equal the overall charge, which is negative 2. I get x minus 8 equals negative 2. I solve for x, and I get x equaling plus 6. Okay. You now have the oxidation state for sulfur. Why is this kind of interesting? What was the charge on sulfur? You're used to seeing the charge on sulfur being minus 2. Why is this not an exception to that? This is not the charge on sulfur. This is its oxidation state. They are two entirely separate things. In certain circumstances, they happen to be the same. Other circumstances, they don't. Okay? So you are responsible for identifying the oxidation state for every single element. Okay? As we started to allude to, we are looking at reactions, right? Coupling two reactions with each other, a reduction and an oxidation. How many of you know what reduction means?
Reduce.
Reduced, fair enough. Okay, how many of you know what oxidation means?
Oxidize.
Oxidize. Okay, a way to solve for our definition with the definition. We haven't defined what those are yet. So what we need to go through and do is look at a reaction and see what goes through and happens as we deal with our oxidation states. Okay, so we've got a more complex reaction here, and I'm going to run under the assumption that you guys can't write or memorize that fast. I want you to go through and solve the oxidation states for all of the elements. Okay? I'm actually going to erase this too. Can't see that. So, spend the time. We only got 6 questions to solve here. Only 6. Okay. And theoretically on an exam, these 6 are solved in under 2 minutes. Yep. Under 2 minutes. Now at under 1.5 minutes. It's not true. Oxidation states. Oxidation state of every single element. If you got a question, raise your hand. I'll come to you and get you started.